Hello everyone, I am Samuel Tidoro, and today I will be presenting to you this newer IPS 2020 paper called Robust Accurate Stochastic Optimization for Variational Inference. Here's the flow of my presentation. I will start with the introduction. So Bayesian learning has recently gained popularity because of its in the machine learning world because of its flexibility and theoretical foundation in probabilistic reasoning. In Bayesian inference, our main objective is to approximate a posterior distribution given a parameter of interest using some given data. Now, variational inference has become a more commonly used method in large-scale approximation inference, due mainly to its computational efficiency. So here we compute for an optimal variational approximation Q star given by the following expression. And the variational family is often parameterized by a vector lambda in Rk so that the parameters of Q star is given by lambda star argmin lambda in Rk of the divergence of Q lambda and P. And recently, there have been two developments that have greatly increased the scope of applicability of variational inference methods. Namely, they are the stochastic variational inference and the black box variational inference. Now, stochastic variational inference allows scaling to large datasets because it tries to solve lambda star using stochastic optimization with mini batching. On the other hand, black box variational inference is quite flexible because it has extended variational inference to a wide range of models because it removes the need for model specific derivations. However, despite these two optimization methods, there are still drawbacks. Namely, one, it is difficult to solve when these methods are quite difficult to solve when the dimensionality of the variational parameter lambda increases. And number two, these existing optimizers are quite fragile. By fragile, we mean that they have so many hyperparameters that we need to tune and that they can fail badly. So, as a solution, this paper tries to address the shortcomings of the current stochastic optimizers for variational inference by viewing the underlying optimization algorithms as producing a Markov chain. So by using this perspective, it allows more accurate variational parameter estimates by using iterate averaging. I will be explaining more on iterate averaging in the succeeding slides. However, despite using iterate averaging, the problems of fragility still remain. In particular, there is a need for us to determine one, when to start averaging or when the optimizer has failed, and number two, there is a need for us to determine when to terminate the optimization. And to address the first problem, this paper proposes using the R-hat diagnostic. And to address the second problem, this paper proposes using a novel stopping criterion called the Monte Carlo Standard Error or MCSE estimates. Let us now take a closer look at the proposed method in this paper, which is viewing the stochastic optimization as producing a Markov chain. And as I have mentioned earlier, in this paper, they tried to improve the optimization accuracy using iterate averaging. They constructed a more accurate estimate of lambda star, which is given by lambda hat, which is equal to the mean of lambda t plus I. Here, our aim is to choose t greater than or equal to t0 and Our T0 is the point when we will reach stationary distribution. And aside from improving the optimization accuracy using iterate averaging, in this paper they also tried to make iterate averaging more robust by one, of course, determining when to start averaging, and number two, when to stop the averaging process. So as I've mentioned earlier, they determined when to start averaging by using the R hat statistic, or basically they tried to determine the value of t using the value of small letter t by using the R hat statistic. So our R hat statistic is a canonical way to determine whether a Markov chain have reached stationarity. And usually in standard processes or standard approach, we try to compute R hat using multiple Markov chains. So given j chains and iterates in each chain and lambda ij such that I is from 1 to n and our j is from 1 to capital J, our r hat is equivalent to the square root of v hat over w hat, where our v hat is the between chain variance and our w hat is the within chain variance. Moving on, they also tried to determine when to stop averaging by introducing a novel stopping criterion called the MCSE, or the Monte Carlo Standard Error Estimate. It is given by MCSE of lambda I equivalent to the square root of V of lambda I over ESS of lambda I. Here, our V of lambda I is the variance of the ith component of the iterates, and ESS of lambda I is the estimated sample size, which is equivalent to Jn all over the quantity of 1 plus the summation from t equals 1 to infinity of 2 rho t. And in the previous expression, our n is the number of iterations after our r hat converges. And our rho t is the autocorrelation of lag t. Now that we have seen, or we have taken a closer look at the proposed method, we can now take a look at the experiments and the results of their experiments. So the proposed method is summarized in the algorithm shown on your screen. Here, they used a learning rate input. They used inputs. The following inputs. The learning rate eta is set at 0.01. The window size W is set to 100. The R hat cut of tau is equal to 1.1. The MCSE cut of epsilon is equal to 0.02. The ESS cut of E is equal to 20. The optimization runs J is equal to 1, and they use the RMS prop optimizer. Furthermore, they use the multivariate Gaussians, where our L in the expression shown on your screen is the Cholesky decomposition of the covariance matrix. And as for their data sets and models, they use the logistic regression on 3 UCI datasets, namely the Boston, Wine, and Concrete, high-dimensional hierarchical Gaussian model, or RADON, 8-school hierarchical model, and finally, the Bayesian network model with 10 hidden units and 2 layers to classify 100 handwritten digits from the MNIST dataset. Now, as for the metrics they measured, the ground truth posterior moments, or the mean mu, and the covariance matrix sigma are estimated using the dynamic Hamiltonian Monte Carlo algorithm. Now, after they computed for these values, they used them to compute for the normalized moment distance d, given by the following formula. And here, our d mu is equal to the L2 norm of mu minus mu hat, and our d sigma is equal to the square root of d sigma minus sigma hat. And here our mu hat and our sigma hat are the variational estimates of our posterior mean and our covariance. So here are the experimental results on the real data comparing the delta elbow stopping rule and the proposed MCSE stopping rule. The star or the asterisk denotes that the convergence was not reached after T max iterations. And as you can see, in the paper, they were able to empirically show that iterate averaging improves the variational parameter estimates. As you can see, in almost all of the cases, iterate averaging outperforms the last iterate in terms of both the moment estimates and the approximations k hat value, if you will focus your attention on the numbers which are in bold. And secondly, they were able to show that the MCSE stopping criterion improves robustness and accuracy. In the same table, we can see that early termination or small value of t in the delta elbow criterion results to less accurate posterior approximations in terms of moment estimates and k hat values. Meanwhile, even with only a third of the total number of iterations, the MCSE criterion or stopping criterion produces a k hat statistic less than 0.05, 0.5. And with the exception of course of radon, and our the same stopping criterion was able to generate or produce a more accurate posterior mean estimate. And as a conclusion, this paper proposes a more robust and accurate stochastic optimization framework that views the underlying optimization algorithm as producing a Markov chain. This framework or this perspective includes a diagnostic to determine a convergence, and second, a novel stopping rule, which are both robust to noisy evaluations of the objective function. And in their experiments, this paper was able to empirically show that the proposed framework or method works well on a diverse set of models and data sets. With that, I am ending my presentation. Thank you so much, everyone, for listening.